The Church-Turing Thesis is a cornerstone of computer science. It helps us understand what computers can and cannot do. This principle connects mathematics to computing. It has shaped the development of technology. It asserts that any problem solvable by an algorithm can be solved by a Turing machine. Understanding the Church-Turing Thesis is crucial for grasping computation. The Church-Turing Thesis is named after two brilliant mathematicians, Alan Turing and Alonzo Church. They worked independently in the 1930s. They made groundbreaking contributions to the field of theoretical computer science. Alan Turing, a British mathematician, is widely considered the father of theoretical computer science and artificial intelligence. He formalized the concept of an algorithm. He introduced the Turing machine. This simple yet powerful model revolutionized our understanding of computation. Alonzo Church, an American mathematician, developed lambda calculus. This is a formal system for expressing computation. It is equivalent in power to Turing machines. Church's work provided a different perspective on computability. It complemented Turing's approach. Together, their independent research converged on a profound idea. They realized that different models of computation, despite their differences, had the same computational power. This realization formed the basis of the Church-Turing Thesis. The Church-Turing Thesis is deceptively simple to state. It says that anything that can be computed by a Turing machine. This statement has profound implications for our understanding of computation. Imagine you have a problem to solve. Maybe you want to sort a list of numbers. Perhaps you want to find the shortest route between 2 points. If you can write down a set of instructions, an algorithm, to solve this problem, then a Turing machine can solve it too. This doesn't mean that a Turing machine is the most efficient way to solve a problem. It simply means that if a problem is solvable by any means, it is solvable by a Turing machine. This fundamental idea connects the abstract world of algorithms to the concrete world of computers. The Church-Turing Thesis doesn't tell us how to solve a problem. It doesn't tell us how long it will take. It simply tells us that if a solution exists, a Turing machine can find it. This profound idea underpins our entire understanding of computation. Section 4. Implications for modern computing. The Church-Turing Thesis has had a profound impact on the development of modern computing. It guides the design of programming languages. It influences the development of new algorithms. It shapes our understanding of the limits of computation. Every time you write a computer program, you are implicitly relying on the Church-Turing Thesis. Programming languages are designed to express algorithms. The Church-Turing Thesis tells us that these algorithms can be implemented on a Turing machine and therefore on any computer. The development of new algorithms relies heavily on the Church-Turing Thesis. When computer scientists design a new algorithm, they need to ensure that it is computable. They need to know that it can be implemented on a real-world computer. The Church-Turing Thesis also helps us understand the limits of computation. There are problems that are simply not solvable by any algorithm. These problems are called undecidable problems. Understanding the Church-Turing Thesis helps us identify these problems. Section 5. A lasting legacy in the digital age. The Church-Turing Thesis continues to shape the digital world we live in. It influences the development of artificial intelligence. It guides research in theoretical computer science. It remains a fundamental principle in our understanding of computation. Artificial intelligence researchers strive to create machines that can learn and solve problems like humans. The Church-Turing Thesis provides a framework for understanding the computational capabilities of these machines. Theoretical computer scientists continue to explore the implications of the Church-Turing Thesis. They develop new models of computation. They study the complexity of algorithms. They push the boundaries of our understanding of computability. The Church-Turing Thesis, though formulated decades ago, remains startlingly relevant. As we venture further into the digital age, this principle continues to guide our understanding of the power and limitations of computation. Section 6. The uncomputable and beyond. The Church-Turing Thesis highlights a profound truth. There are limits to what can be computed. Some problems are simply beyond the reach of any algorithm. These uncomputable problems challenge our intuition. They inspire us to explore the boundaries of what is knowable. Imagine trying to write a program that predicts whether any given program will eventually halt or run forever. This is the famous halting problem. It is an example of an undecidable problem. No algorithm can solve it for all possible inputs. The existence of uncomputable problems is both humbling and inspiring. It humbles us by revealing the limits of our computational power. It inspires us to explore new ways of thinking about computation. It challenges us to find creative solutions to seemingly impossible problems. The Church-Turing Thesis, while defining the limits of traditional computation, also opens up new avenues of exploration. Quantum computing, for example, operates on principles that challenge the classical assumptions of computability. As we explore these new frontiers, the Church-Turing Thesis serves as a guiding light, reminding us of the profound relationship between mathematics, computation, and the universe itself.